Okay, so again, good day to everybody. Welcome to SRU's presentation titled The Power of a Tuned SRU Dynamic Simulator. Definitely we're most pleased that you could join us today. Definitely simulations or webinars, I should say, these presentations are something that we're starting to do here at Sulfur Recovery Engineering. We understand that a lot of people kind of know what's going on with some of the tools that we use to provide solutions to them, but everybody's always interested to learn more. And we're definitely here with all our solutions, all our tools, and all our expertise on sulfur recovery units. We want to definitely provide that to you. My name is Inshan Mohammed, and presenting with me today is SRE simulation specialist Dharmesh Patel. I'll be doing some introductions a bit later into both of us, and we definitely hope that you find this session informative and helpful. So let's get straight into it here. This webinar, like I said a bit before in the intro, is based on the paper of the same title that we presented at SOGAT 2015. That was in Abu Dhabi earlier this year. We've modified the presentation to also include time to demonstrate the creation and the use of dynamic model. And we'll try to keep the presentation hopefully within 40-45 minutes so that we have a sizable question answer period at the end. In short, here at a glance, what we're going to be covering is in the introductions, we'll be covering introductions to the presenters, to tune dynamic simulations, and to the objectives of the SOGAT paper, kind of linking it in with the paper that we did. Also, we'll do a demonstration on how to create the tuned dynamic model. Number 3, we'll do the analysis created by the tuned dynamic models to achieve the objectives of the paper. So we'll go through that. Number 4, other uses and capabilities of a tuned SRU dynamic simulation. And finally, we'll have some concluding remarks about the paper and about dynamic models in general. So introductions. Myself, like I said, Inshan Mohammed, I'm a professional engineer with the Alberta and Quebec Association of Engineers. I'm the principal process engineer here at SRE. I've participated in over 50 different sulfur recovery unit projects, with a large number of them being startups or shutdowns of an SRU. As you know, it's easy to control or troubleshoot a unit when it's operating at steady state. Everything's lined up, everything's nice and straight. However, that task becomes much more complex when the unit is operating outside of that steady state, in a state of dynamics. My co-presenter today, Mr. Dharmesh Patel, he's SRE's Senior Simulation Specialist. We certainly are thrilled to have someone of his caliber working with us. His 10 years of process engineering experience have made him highly proficient in the use of VMG Sim, as well as AspenTech HYSYS simulation software. Mr. Patel has completed over 20 different SRU dynamic models here at SRE. And of course, practice makes perfect, and we've solidified our capabilities with creating tuned SRU dynamic models. And hopefully this presentation will share some of the secrets with you and generate your interest with it. A little bit about SRE, Sulfur Recovery Engineering. Since 1998, we've been helping refineries, gas plants, and engineering companies worldwide to achieve the optimal performance of their sulfur recovery units. We're a specialty services firm, and we've centered around providing consulting to help with SRU design, engineering, and commissioning. And also we provide lifelong SRU servicing, which includes SRU performance evaluations, troubleshooting, shutdown, and startup assistance, as well as debottlenecking services. And with that lifelong SRU servicing, we have a proprietary gas sampling and analysis methodology, which allows us to quickly identify all of the sulfur compounds present in the inlet, outlet, and interstage process streams within the SRU. Allows us to do that troubleshooting and performance evaluation very well. Now a little bit on why you would probably need and should need a tuned simulator. So Normally, an engineer is using a simulator to predict what will happen at the outlet of a unit operation. In particular, in the sulfur recovery unit, with its thermal and catalytic stages, those predictions are made by way of correlations. Obviously, the more data in the correlations, the better prediction. We use here at SRE VMG Sim as for our dynamic simulations, VMG Sim Dynamics. And VMG Sim does have all of the 15 plus years of SRE collected data in their correlations, making them highly accurate. But what's the next step after that? How can you change? And when you're trying to predict, say, for example, your SRU tail gas composition, so you've got in a 3-stage, you got your thermal that's doing a correlation. You got your first, second, third, all are doing correlations. And hence, when you're trying to predict what your SO2 emissions are, wouldn't it be better to have your model produce the results that you observed in the field? So this is what we do with a tuned model. Your simulation becomes less of a predictive tool and more of an accurate representation of what happens out in the field. A little bit about VMG Sim Dynamics and tuned dynamic simulations. They're so special because now that you've got a model that's accurately predicting the compositional analysis, then you could go ahead and add into that the equipment specific information, add on top of that the control logic, and what you end up getting is a complete offline sulfur recovery unit. With an offline tool, now you can accurately determine outcomes of various scenarios. We can study the effects of operating the SRU outside of normal daily operation. And this will be completely without the worry of emission violations. You don't have to worry about getting that slap on the wrist because, oh, well, I wanted to operate my SRU at maximum capacity just to see what would happen. Next thing you know, I realized something was undersized. My SO2 emissions went out of whack, and now I have to pay a fine. No, all of that can be done with this complete offline SRU tool, the tuned dynamic simulation. Another thing we could do is we could study the capacity and equipment pinch points of the SRU through variations of feed flow and or composition. A lot of people answered that yes, they're experiencing a downturn and they want to know. Well, a tuned dynamic model can allow you to study those pinch points with changes to your acid gas composition. Also, we could study startup, shutdown, and operating procedures through case studies. And for example, we could set up an operating scenario to train board operators. We'll show you a little bit in this presentation some of the tools in VMG Sim Dynamics, which allows it to look and mimic exactly what a board operator would see. And Mr. Patel is going to be illustrating that for us. So there's really a lot that you could do with tuned dynamic simulation. And so to hone in on a particular case, what we'll be doing is kind of focusing on the paper that we presented at SOGAT. So going back to this paper, the purpose of the paper was to determine the effect of changing feed on the equipment performance of a 400 tons per day SRU. And we're investigating 4 items in particular with the various dynamic simulation cases. 1, we're going to look at the effect of the SRU's processing capability. 2, identify any equipment pinch points. 3, observe the blower's performance. And 4, commenting on the control's logic's behavior and performance. The layout that's being used in the paper, a 3-stage modified Klaus SRU with a direct-fired fuel gas reheater in the first catalytic stage, with indirect steam reheaters in the remaining 2 stages. The acid gas feed being used, low quality, H2S quality of approximately 44 moles %. So now I'm going to pass on the floor to Dharmesh, who will present an overview of the tuned SRU model in VMG Sim Dynamics, and who will show us the acid gas composition and feeding the model.
Hello, everybody. I'm Dharmesh Patel from Sulfur Engineering. I'll give you a little bit heads up and overview about the case what we have and what we presented at the SOGAT. Here is a PFD of the model with the blowers, control valves, controllers. Here are the reaction furnace. The steam boiler follows with the three class catalyst, where the first one has a direct fire reheater and remaining two converters have indirect reheaters. And furthermore, we go in more details as we go further on these cases. But this is just an overview, and let me show you one more thing is acid gas composition. What is a typical acid gas composition, what the case was made for. Over here, the H2S concentration is around 44%. That's not really good quality acid gas. And on a different scenarios, we studied like a different composition plus different flow rate for the same model. Okay, I'll hand over further to the Inshan, and we'll talk in detail as we go on further.
Thank you, Dharmesh. So getting back to the paper, 4 different simulation cases or 4 different changes to the SRU acid gas feed stream were investigated. These included 1, operating the SRU at 410 tons per day with the same low quality 44 mole percent H2S feed. Case 2, operating the SRU at the lowest turn down capacity with the same acid gas feed. And cases 3 and 4 were repeating cases 1 and 2, but now this time with a 40 mole percent H2S feed. For conciseness, this presentation is centered around case 1. If you're interested in the outcomes and details regarding cases 2 through 4, you could definitely contact us. We'll be able to provide to you our paper that we presented at SOGAT. So now let's go ahead and illustrate how we created the tuned dynamic model. So the first step in everything is data collection. So you need to collect information with regards to how the unit's performing in its current capacity. So what we had to do is collect interstage gas compositional data from the thermal and catalytic stages. And going back to SRE's bread and butter is that we are capable of collecting these high H2S content streams. Most analytical companies don't want to touch H2S at all. So we have capabilities of collecting these samples safely as well as analyzing them quickly. And that's the first step in getting this tuned dynamic model, is to understand and collect accurate results for each process gas stream and throughout the SRU. Also, we want to collect a good pressure profile of the SRU as necessary. Next thing is the data mining exercise. This is pretty much worthwhile on its own because funny enough, every time we end up going to do a dynamic simulation, it seems that unfortunately the operating companies, even though they receive the information from an EPC or EPCM or design company with as-built drawings or with regards to any other type of documents that would have the information necessary for the dynamic model, it strikes me as odd that every time we go there, it ends up taking a long time for us to actually pinpoint all this data. So that could even be a worthwhile exercise on its own to just get that. Third piece of information that you need in order to collect the necessary data is the control narrative of the SRU, how everything is being put together, as well as the tuning parameters of the control valves. Once you've collected all the data, then you go to step number 2, which is create the model. You need to gather all the information ahead of time. Obviously, it doesn't make sense to start creating the model without having all data present. And with that, I shall go ahead and pass the microphone off to Dharmesh. He'll be showing us how we can tune the reaction furnace to satisfy the data. As well, he'll show some of the valve information that we've got in our model right here.
Okay, thank you, Inshan. Okay, so here I'll give you a little bit glimpse on how we really created this model, like what really information makes difference from state to dynamics model. Like as Inshan mentioned before, like we do collect the samples on the normal run of the plant, and from each stage of the process, for example, reaction furnace, catalytic converter outlets, and all those things. And along with that, we also take the pressure profiling of the plant with maximum sample available. So in that case, for example, the reaction furnace here. So here, as you see, like we have set up the new parameters here, then just default correlation use. These parameters we obtained from our result, and then we tuned up in our steady state model to come up with how this reaction furnace is behaving. So while we go for further predictive model on different scenarios, this will help us at certain extent. Second thing was that the converters. In our converters, we also have the same way like I showed you the reaction furnace, but with the different ratios and scenarios, our SRU correlation model predicts even better results. So in this case, we use SRU correlations. So the reason using that is that we have to run this model on different scenarios, not only for flow rate, but also with different composition of the acid gas. And at that time, this model predicts more better results. The third, as Inshan mentioned, we had to collect lots of data to function in this dynamic model. So you might be wondering what kind of data and how it's really affecting. So for example, if you see the reaction furnace, we have to get the geometry and other information of it, which kind of help us to predict residence time on it. Plus, same thing with the condensers and converters, because those geometrical informations also correlates with the pressure drop tuning parameters. As I mentioned before, we also collect the pressure drops at different stage of the process. So considering that, while you have turned down or turned up, we noticed that it's really closing and really matching closely to the real-time plant data. Other things I would like to also mention is, for example, valves. So the valves has a, just to give you a second here, okay. So here in this model, like we collected the data from our client regarding valve curves, its characteristics, sizing, and stuff, and we incorporated those things here. So even creates a really high fidelity model in terms of the behavior of the valves, and it also help us to come close to the real tuning parameters, which they really want to know, like if they have turned down or turned up scenarios, what would be the ballpark range for the tuning parameters, so they don't have to wander around too much on it while they go for those changes. Other considerable information we also inserted is in terms of the blower curves. Like we are fortunate that we are able to get the performance curves for the blower, and we also incorporated them in this model. So these things are also important in terms of when there is a turn down scenario specifically, because in that condition you can also study at what range your blower is performing. For example, over here, Like this is a 400-ton design plant. I'm running this one right now at 200 tons, and it's approaching a near surge limit. So all these studies you also can do while you are running the model once it is properly lined up. Other thing is that we also incorporated the control narratives and other algorithms regarding air demand controls from vendor, and that's also matching up nicely. But some places it is not 100% right, so we have to add up the factor of those calculations to match up the real performance. So that's indication is that they can also modify their burner strategy, or they also need to revisit their control algorithms. Okay, and further, I will also go a little bit here explaining there is a few stuff a little bit different than normal plants we see here. Is if you see here, like they have two main control valves on the main air demand and one trim air valve. Like some other plants, you might see just one control valve. So all this information is really handy and helpful when there is any emergency shutdown or any equipment failure, for example, any valve shot, or they want to replace it. So they can configure those equipment here, put those new valves, CV codes and other data, and see how it behaves in case of it is not identical what they are replacing. So definitely we'll talk further about in detail, but I'll show you one more thing about the flow sheet. Just give me a second here. Okay, so this is like a controller. It has a different tuning parameters, but as Inshan mentioned, like this model can also be used for training purpose for the plant operator. So like this is a typical faceplate, so it looks like similar or very close to delta V what we see on DCS control panels. So while you make any changes, these things also represents how those changes behaves and reflects over here. So it's really like a familiar term for plant operator as well. So furthermore, let me go through one more step. There is also other characteristics you can study. It's a strip chart and other things, but we'll go further in details. And right now I'll hand over to Inshan.
Thanks, Dharmesh, for that overview of the tune dynamic model. Definitely a lot of information that can be put in, and definitely a lot of information necessary in order to create the tune dynamic model. For completeness of the presentation slides, which we can provide to you afterwards, we've included here in the presentation specific information with regards to the models and for the paper. These were the tuning parameters used for the model. Again, the tune dynamic model has the ability to have what's called faceplates. And this image right here is just an overview of the controller faceplate option that you have in VMG Sim Dynamics. We definitely really like it because it allows that, and just as Dharmesh mentioned, it allows that familiarity with control board operators. And so what you can do is set up your flow sheet or set up your operating scenario to include the faceplate as well as the flow sheet, so that when they're doing the operating scenarios and learning how to what happens during these scenarios, at least there's that flexibility and also familiarity, which is essential. And that adds that other thing. It's that, okay, dynamic models, you believe that it's an engineering tool only. But what's nice is that okay, you go ahead and you get a tuned dynamic model created for your SRU. Well, now you're able to get more value out of it. Not only do you use it within the engineering part or design, you can go ahead and utilize the same model and use it for training, use it for people at the operations. And so if you're in an EPC company, it ends up adding more value to your product line, because not only are you doing the engineering design, but now you can tell your client, well, now I can add in more items. I could train your operators using the same model. And if you're an operating company facing downturn, well, not only are you solving your problem on how to incorporate or plan for the turn down, but you can also use that tool in order to train your operators. So, every day we're looking for more ways to save on the dollar. And we definitely believe that the tuned dynamic model, especially with this faceplate option and the training for operators and engineers on site, adds that value to the model. Now we have a couple of PFDs of the tuned dynamic model. Again, this is for completeness of the presentation. Again, this shows you in the presentation slide the blowers, the controllers, the valves, reaction furnace, and everything, how it looks in VMG Sim. This is the second screenshot. In this one, we're seeing the waste heat boiler, the 3 converters, the DFR, sulfur pit. Now we'll move into the presentation, talking about the analysis of the simulation cases that we did in the paper. In case 1, normal operation was 16 million standard cubic feet per day of acid gas feed. So, as you recall, case 1 was operating the unit at 410 tons per day. That was the calculated maximum capacity of the unit. With the 44 mole percent feed, that translated into a 24 million standard cubic feet per day acid gas feed. The time that it took for the model to reach steady state was 20 minutes. So definitely, with regards to reaching steady state, there wasn't major hiccups or anything like that observed when we pushed the unit to 410 tons per day. Some other observations that we found was that the RF residence time was 1.97 seconds, well above the industry standard or minimum required for complete combustion of all catalyst contaminants. Another point that we observed for case 1, condenser 3 was found to be at its design limit. We defined the design limit of a condenser in terms of process, gas, mass, flow, velocity as 5 pounds per second per square foot. And obviously 400 tons per day was the calculated maximum that the unit can operate. So the equipment pinch point was condenser 3. A couple other points: catalytic converter gross hourly space velocity was 575 inverse hours. All other equipments appeared okay. All other control operations and valve operations seemed to be working well. Dharmesh alluded to a strip chart capabilities. Again, this is further enhancing the VMG Sim Dynamics capabilities of training operators. And I like the strip chart because it's very visual. I'm a very visual person, can see exactly what's happening. Here, this is the strip chart illustrating case 1. We notice the acid gas increasing up. We have our first blower ramping up. Oh, we need blower number 2 to ramp up at the same time. And then in green here, we have H2S and SO2 at the outlet, condenser 4 outlet. And we notice that the spike that happens, and approximately less than, at this point, 12 minutes. There's some other factors that we had to look at, totaling the full 20 minutes to reach steady state. And this was the detail and strip chart illustrating case 1. I'll pass the floor now to Dharmesh, who will show us exactly doing a similar step change, how that looks in VMG sim dynamics.
Okay. Hello. Thank you, Inshan. As I mentioned before, this model was lined up for like 200 tons per day during a turndown capacity. And we'll make a couple of changes and see how this model behaves. So it gives you a little bit idea like why we need a dynamic model than just steady state. Sorry, it's freezing up here a little bit. Okay. Okay. So, for example, as I mentioned before, like while we run the plant at particular steady state or normal operations, at the same time we also take a pressure profiling. The real reason for taking that is that using that information and DCS data as another parameter, we kind of set up the pressure drop tuning parameter for each equipment, which kind of represents like for particular flow rate, what would be the pressure drop across the equipment. And that's really helpful information because while we go for different scenario study, it helps us to see what would be the pressure drop, what would the pressure along the pipelines, and that eventually give us idea of what will the velocity. Because so many of our clients wants to check all their guidelines, like during different scenarios, if there is any guideline is violated or not. For example, some clients has a maximum velocity should be in a piping at any stage should be X amount, or if the condenser has a maximum velocity should be Y amount, or the gross overlay velocity throughout the condenser should be not reach more than that or other. So all those parameters are designed for those guidelines. We need to check if different scenarios we are running, if those will match or not. And that's when this model really helpful. Second thing, we will see a little bit how those changes we make and how it reflects here. So for example, let's go up here. It's a 200 tons. Let's go for 300 tons per day capacity. And let's see how it will behave. Historian strip chart. Okay. So this is a strip chart here. Okay, so this is a step change we made, and it shows us the green symbol is a air demand ratio, H2S SO2 ratio, and these two guys are main air through valve A, acid gas and standard, then acid gas through valve B, RF trim air, RF main air. So these things are right now following whatever is the correlations or control algorithm the plant is using right now. So here you can see at certain point the ratio exceeded certain amount like 5, but you have, when you are studying different scenarios, you want to make sure like what step change you should go with, because this will give you a little bit help like your ratio is really going off up to what limit, because if your ratio is really too much off, it could create a sulfur fire plant or in the pipings. So you got to make sure like what step change you should go, and you can study all those things from the straight chart as well here. This is also helpful to determine what is the tuning parameters you want to set up along the way. how much sensitivity you are looking for. So all those studies you can, this is not just only for process operator, this is also useful for instrumentation guy as well. And as the tuning parameters are also subjected to sometimes personal preferences of particular operator, how quickly, how closely they want to get those results. But definitely, I really like this parameter over here. Like you can see it's steadily going, or it has those sinusoidal curves or what. So that's how we lined up the tuning parameter, and for particular different scenarios, we also suggested those tuning parameters for which scenario they are running, what would be the ideal or ballpark range for them. So whenever they go for those step size changes in a plant, it's very easy for the operator to bring that model in a steady state quicker than just running the model for a longer time, running the plant for a longer time on upset conditions. One more thing we can also see that the behavior of the blower. So as I mentioned before, like while I was running this plant at 200 tons per day, it's a really turned down condition. It was operating right here at the surge limit. But right now, this is the green dot is the real operating point for the blower. So it also gives a little bit idea about how your blower performing that particular scenario. Second thing I would like to also mention is that as the flow rate and scenario goes on, if you notice the pressure is increasing along the pipeline. And furthermore, let me show you one more thing here. In a process calculator, this is a really wonderful tool which I really like in VMG is by using this calculator, you can correlate all those control logics and narratives they had put it here. For example, if you change your composition of the acid gas, this will help you to make sure your really air demand calculation is according to your control algorithms. If it is not, or if it is not giving you right amount, then you can consider the factor of that calculations, and you can also advise instrumentations to upgrade that algorithm there. And these things we noticed at our client, and it really helps while we are solving this model for. Okay, that'll be it, and definitely you can ask us later on any questions you have in this regard, and we will be glad to help you in that. I'll hand over to Nishan for further discussion.
Thank you, Dharmesh, for that. It was definitely wonderful, and to me, it's good to have a webinar and present our simulation case and present a PowerPoint presentation. But it really goes a lot further when you can see the model in action and see exactly what's happening with the model. See it visually, it provides that extra element. But continuing on with the presentation, to summarize quickly for the remaining cases 2, 3, and 4 that we did with our paper at SOGAT, we'll quickly just go over the conclusions from them. In case 2, when we tried to operate the minimum acid gas flow rate that we were able to achieve with 44 mole percent H2S feed, that was determined to be 277 tons per day. In this case, the 4th condenser reached the lower design limit of 2 pounds per second per square foot. So now we were able, so for this particular scenario, this 400 tons per day plant, turn down was defined as this limit, design limit, and the processing capability of the unit ended up being calculated as 277 tons per day. In case 3, with an H2S quality of 40 mole percent, Operating the SRU at 410 tons per day resulted in a flow rate of 26 million standard cubic feet per day. In this scenario, the third condenser was found to be exceeding its upper design velocity. So now we were going above that upper limit of 5 pounds per second per square foot. Finally, in case 4, again with the 40 mole percent feed, the SRU is capable of processing at a minimum 260 tons per day. Makes sense. Lower quality acid gas allows you to get to a lower processing capability. So that's it for the paper. And the presentation that we've done, the paper and the conclusions received from the simulation cases. Now let's move on to other uses of a tuned dynamics simulation. We've gone ahead and alluded to some of these ahead of time, but we'll go ahead and repeat them now. Other uses, like we said, similarly for this paper, identification of pinch points of various plant inlet changes. Another thing is the retrofit or addition of equipment. Now, you want to know, okay, we need to replace valve A on the main air line, but we don't have the same valve A anymore. We've got model XYZ instead. How is this going to affect my changes, or how is this going to affect my SRU? Well, you just put in the information into your tuned dynamic simulation. You're able to identify how the unit is going to be operating, and also identify what changes you need to make to the tuning parameters to set up the exact same control that you needed to have, or that you had with the first type of valve. It's very easy to do that. You can change your equipment information very easily with the model. Third example of what you can use the model with, and we demonstrated that quite a bit in this presentation, is training. You could train your engineers, you could train your board operators, you could have simulation cases at SRU. We can set up those simulation cases for you to be able to train people. It also adds value. You're presenting, you're paying for a tuned dynamic model, or you're getting one created, or you're creating one in-house. Well, it adds value that you're able to gain some training out of it, or gain some other uses other than maybe modeling or seeing what's going to happen in your turn down scenario. And finally, that goes into that is simulating plant upsets, startups, or shutdowns. So with that, we'll go ahead and conclude our presentation. Like we said, the main driver for the paper was the perceived changes to the acid gas quality to the SRU. You want to understand, this is my plant. How is it going to run when hitting my maximum capacity? 400 tons per day plant, you would expect that there's going to be a 10% design margin, which means that you should be able to operate at 10% of 400, should be 440. In this particular case, we weren't able to. With the design considerations put into the tuned dynamic model, we found that it could only reach 410 tons per day. Very interesting. Also, what happens with my acid gas, or what happens to my SRU when I have a turn down scenario? How low can I go and still be within the design accepted parameters or limits? In this case, we found 277 with the current acid gas quality. So that was the main driver of the paper. Summarizing, we also did and illustrated other uses for the tuned dynamic simulation. Going over points 2 and 3 here, prime importance was to evaluate the SRU's capability, max tonnage, min tonnage, just talked about that. We also talked about the control logic capabilities to satisfy those changes. And then again, in this particular case, condensers 3 and 4 were identified as equipment pinch points for the max or the minimum. So with that, we want to thank you for your time. We have 10 minutes or so for questions. in general, SRE can be retained to assist you with your SRU dynamic model and provide training on how to use the model and gain the most benefit from it. I do hope that you found our webinar informative. I do encourage you to fill out the survey at the end of this webinar when you exit, and you'll be reminded of that via email as well. We do appreciate your feedback. Like I said, this is the first of hopefully many that SRE is going to be presenting, and we definitely want to have a good quality presentation that's a benefit to our users. So we'll go ahead and open the floor to questions. We do have quite a people in attendance, so maybe just either raise your hand and I could direct it, or you could ask your questions out loud. I'll be unmuting all the microphones now. Was the presentation that good? Nobody has any questions? You could feel free to type them if you want to in the chat box. Anybody have any comments? Everybody just shy? If you're shy, feel free to just type in your question. I'll definitely answer them or try to answer them here. Somebody's typing something. Is this okay? So could these models be used for investigating things like the effect of a waste heat tube rupture? Yes, it can be used to investigate those problems. We have another question here. Is the model, so that's the simple answer, sorry, to that, is that the model can be used, yes, to investigate waste heat boiler tube ruptures. Another question that came in, is this model available for folks who are interested in kicking the tires themselves? This particular model, no, but we can definitely help anybody out who would like some type of model in order to play around with. We can help them create one in particular and assist them with that. Shashank, you had your hand up here. Go ahead. Your microphone should be on mute if you want to ask your question verbally, or you could type it in. Okay, so we have a question here saying, how was the pressure drop at various capacities for the equipment, such as condensers, calculated? I'll pass the floor on to Dharmesh, and he'll be able to answer that question in more detail.
Hi, Shashank. Okay, so as I mentioned before, during a particular steady state run or stable run, we took a pressure profiling across the plant for that conditions, and after that, for each location what we took a pressure reading, so we considered that as a one block, and in that consideration we considered the pressure drop across the equipment plus from one block to the other block, the piping pressure drop as well. So we consider it's, for example, you have condenser one outlet to converter one inlet. So that's considered one a block. The in and out pressure drop we
Needs my
measure
computer,
for
but I
particular
carry it
fluid
always. I don't know why I
for
asked.
particular operations, and then we dynamically tune the pressure drop tuning parameter in dynamic model.
Setting this
And
back,
once the pressure drop tuning
model
parameter
can share with
evaluates,
me, Amanda.
after that it's
It's not going to
stabilized,
be
and
for
once
that
you run
same
that
system.
different
It's a
scenario,
different
that
system,
tuning
but
parameter
you're
generates
going to
different pressure
be
drop
doing some of
for
that.
particular different
So
pressure and
work for
flow
you.
conditions.
So you have a
I hope this will
your
help you a little bit.
notes and everything. And let me turn this off.
Okay, so he's saying that there is an audio overlap. I'll try to repeat the answer here. What it is basically, so when we were taking the gas samples, at the time we took a pressure profile survey of every single point along the SRU. So not only are we getting a snapshot of the compositional analysis, we're getting a snapshot of the pressure profile throughout the SRU, and we would incorporate that data into the model. And then we ensure the high fidelity of the model by incorporating, yeah, and by adjusting the pressure drop tuning parameters. You are very welcome. I'm glad that assisted, helped you out. Keep the floor open. Again, we still have 5 more minutes. I do understand that people might be going for lunch or wherever the case may be, depending where you are. We'll stay on the line here for another 5 minutes. Definitely at this point, if anybody does need to go, thank you very much for your attention. Like we said, we are looking to do more of these in the future. If you have any comments or suggestions in order to improve our presentations, if there's anything in particular that you'd like to have a presentation on, like for example, amine simulation or dynamic simulation for amine units, as we asked the audience at the beginning, feel free to drop us a line. You can always contact us toll free or phone number, email. We're always here to provide solutions, to provide answers. Also, we've got definitely a lot of knowledge that we've gained over the few years of consulting and doing troubleshooting for SRUs. So if you have anything with regards to that, feel free to ask us. Most likely, we have the solution. Are there any more questions? Okay, we have a question here. Was the utility side also modeled? We've concentrated on the process side, but we can incorporate the utility side if necessary. So the short answer to that would be no, but it can be done. Another question coming in: have you ever done a biomass combustion simulation with VMGSim? Me myself, I have not done biomass. Mr. Patel here is saying that he hasn't done one either. I don't have the answer if that can or cannot be done. But if you'd like, send me an email and I can get to the bottom of that and answer your question, or get some more possibility. Oh, I got somebody here saying that yes, it is possible to do a biomass combustion simulation. So it can be done. And if you're interested in finding more information, definitely send us a line and we can get you in contact with the right people. And quite possibly, I believe everybody can see the question and answers as they're coming up here. That should be good. All right. with that, I guess we shall call it a day. Thank you again, everybody. If you have any other questions, feel free to contact us. We hope you find the presentation useful. And thank you for your time. Have a great day.